The Hooke's law situation that we just discussed normally applies best to systems that can be stretched rather easily. But if we look at something like just a steel beam and we want to stretch that beam or compress it, then we deal with a slightly different relationship. It's still the same in principle. And what we want to look at is how we distort solids, things like a steel beam, by twisting it, by compressing it with force, or by pulling it apart. And we find that in general, the stress is going to be proportional to the strain within what is called the elastic limit. But let me mention the elastic limit. The elastic limit is that distortion which the system will endure and still go back to its original configuration. You've all seen something like a rubber band. You can pull it, and it'll go back to its original configuration. But if you take something like a paper clip and bend it beyond a certain point, and it doesn't take very much, the paper clip will not return to its original shape. We say then that we have exceeded the elastic limit. And once you exceed the elastic limit, none of these equations hold because you have a new equilibrium position. The first one of these that we want to describe is what is called Young's modulus. A Young's modulus concerns the following situation. We're in section 11.2, and we want to look at Young's modulus. Young's modulus applies when we have, let's say, a solid. This might be a steel beam or something. And it's going to have a certain length. Let's call it L naught. It's going to have a certain area to this face. And we're going to take this in and we're going to attach it to glue it to the wall, concrete or something like that, so it's immobile. And now we want to take this area right here and either extend it by, stretch it by using a force, or we could compress it by using a force likewise. The question is, how much force do we need? Well, if we take it out to a distance, kind of hard to draw this, a distance, let's say delta L, so we're going to stretch it by delta L, the force is going to be proportional to, we're going to write our constant proportionality as Y, which is Young's modulus, times the area. Why is it proportional to the area? Well, if you think about it just a minute, if I had two beams, that would be like twice the area is like having two of these beams. If I had two of these identical beams, then it would take twice the force to extend the system by the same amount of distortion. Therefore, the larger the area is, the larger the force. So it's going to be proportional to how much area I have. If I were to cut the area in half, it would only take half as much because I'd only have to do half the beam. So it's going to be proportional to, that's the Young's modulus, proportional to the area, and it's also going to be proportional to how much I distort it, delta L, as a fraction of the length that I have. So if I distort it by 1%, then that would be a certain delta L over L as 0.01. But if I distort it by 2%, then of course I'm going to have twice the force. So you can see that the force is going to be proportional to the distortion, but it's going to be inversely proportional to the length. Another way to think of it is if the length is twice as long, that same force can distort the system by twice the length, because if I put two of these beams, one end to end, to the other one and attach them and put the same force on it, that same force will stretch this one by delta L and the other one by delta L. Therefore, it would stretch 2 L naughts by 2 delta L. Therefore, it's proportional to delta L over L. This is the equation that's applicable for Young's modulus, for stretching or compressing a beam or a solid. And it's written there in red. And you might wonder, what are these constants like? Well, I've written several of these out. These constants are pretty large, Brass is 9 times 10 to the 10th. A brick is 1.4 e to the 10th. Steel, 2 e to the 11th. Aluminum, 7, 6.9 e to the 10th. So these constants are very large, and of course this is in the metric system where the area would be normally given in square meters. This would be in meters in distance. So in order to stretch this 1 meter for a square meter of something like brick or steel or aluminum or brass, then you can see that certainly this is going to take a huge amount of force. So we might say, what would it take? And here would be a standard problem. We want to stretch a steel beam, and let's let it have a length, L0, equal to 1 meter. Well, let's make it 2 meters. So we're going to make this 2 meters long. That's about 6 feet. So we've got a 2-foot beam. And we're going to stretch that by 1/1000th of a meter. So delta L is going to be 10 to the minus 3 meters. And we're going to take a cross-sectional area here that's going to be kind of small. We'll take our cross-sectional area, our area A, let's let it be 1/100th, 10 to the minus 2 square meters. Okay, let's see what force it would take. That would be like a 1/10 of a meter by a 1/10 of a meter. That's still pretty large. Let's make it a square centimeter. So that would be 100th by 100th. There'd be 1 square centimeter of its area would be 10 to the minus 4 square meters. Now, what would our force be? The force would be, for steel, 2 e to the 11th, for Young's modulus. And we would have times the area, to be 10 to the minus 4, times the length, we're going to extend it, 10 to the minus 3, and we're going to divide by our length L0 here, and that would be 2 meters. Well, the 2 is going to cancel the 2, and we're going to end up with e to the 11th times 10 to the minus 4th, 10 to the minus 3, that'd be 10 to the minus 7th. And there's no power down here because this 2 cancels that 2. 7, 8, 9, 10, 11, so this would be 1 e to the 4th newtons. Well, that's quite a lot. That's 10,000 newtons that it would take to take this beam that's 6 feet long out of steel. It's 1 centimeter squared, 1 centimeter by 1 centimeter, and stretch it out by a very small amount. And the very small amount is 1/1000th of a meter. That's a millimeter. So that gives you an idea of how we would calculate something like that. Also, you could turn that same problem around and use that to compute what Young's modulus would be by measuring the force, the area, the length, and L0. The next problem we want to look at is what is called the shear modulus. Now, for the shear modulus, we have a very similar type of situation. Well, what we want to do is we want to take a material and shear it. Now, how do we shear something? Well, the shear modulus, this would be 11.2b, let's say. The shear modulus means that we're going to take this beam again, let's say out of brass or steel or some material like this, and we're going to anchor this down to the floor, either by glue or vise or something like that. And we're now going to assume that this has a length L0 up this way, an area at the top, A, and now what we're going to do is we're going to take it and try to shear it to the side by a distance, delta L. In other words, it's simply like you shear a bolt off with torsion. Here we're going to shear it in a horizontal direction. And we can again say that the force per unit area is going to be proportional to the strain. And that is the force that's going to be required, force F, to pull it in this direction. Remember, that's anchored down here, so this whole solid is going to bend like so. So we're going to have force is proportional to, and the constant proportionality is S, which is called the shear modulus, times the area, because if it has twice the area, it will take twice the shearing. You can see that immediately because twice the area is just like having a second beam over here, so therefore the force would have to be twice as great, times the distance. So the greater the distance, the greater the shearing. But if it's twice as long, then it would only be half as much. So we divide again by L naught, and we can see that this is very comparable to the formula that we previously had for Young's modulus, proportional to the area delta L over L naught. But here, rather than compressing it or extending it, we're twisting it to the side. This is the equation for the shear modulus. The equation is applied just like it is before, and I only want to point out here some of the examples of shear modulus. Brass is 3.5 e to the 10th. That's kind of comparable to the brass up here. That was 9 e to the 10th for stretching it. So it's a little bit easier to shear it than it is to for brass than it is to stretch it. As for steel, this is about 8 e to the 10th, so it's easier to shear steel. This is 2 e to the 11th, which is just somewhat more. Aluminum, again, is less, 2.4 e to the 10th versus about 7 e to the 10th for the Young's modulus. So you would simply do exactly the same thing that we did before. You can compute the force to shear the system. If you put in the area, you put in the amount of the shear, and you put in the length that you have. Again, we could put in exactly the same values that we had for the last problem and compute this, but now using the shear modulus instead. Now there's another type of modulus. It's called the bolt modulus. And the bolt modulus is how a system compresses when we put it under pressure. And here we can actually compute the bolt modulus not just on a solid, but on a liquid or a gas. Obviously, a liquid or a gas is going to flow. So we can't stretch the liquid, and we can't shear the liquid, but we can take a liquid or a gas or a solid and put it under pressure and say, how does this system compress? So we do that by looking at an object like this. You can imagine kind of a cubic thing. And we could, one way to do it is we could take steel, for example, a block of steel, and we could put it underwater. We could put a piston up here and apply pressure, greater and greater pressure. The pressure is going to be uniform on all sides, on every face of this, so the pressure is uniformly distributed. The pressure is going to be the force per unit area, and it turns out that the force per unit area, or pressure, force per unit area, is going to equal to, because the system always compresses, so they've got a minus sign, times the bolt modulus times the change in volume over the volume. Just like before, we had the change in length over the length. Now we have the change in volume over the volume. So the fractional change in the volume of the system, you notice that this is dimensionless. Each of these is dimensionless. That's the length divided by length, volume divided by volume. And so the pressure that we put on the system is going to be proportional to the change, the percentage change in the volume. We could take this area and put it over here, as we've done before, but it's easier when we're dealing with pressure on a system just to divide through by the area we don't have to divide through here. It's more obvious if we just have an area for the system. But here, we're actually looking at a pressure that we're applying, and so it's easier to take the area, bring it over here, and look at the pressure as the inverse, as the negative of the bulk modulus, B, times the change in volume over the volume. And this is the operable equation here. And if you look at constants that we have here for brass, again, these things are, the values are about 10 to the 10th or 10 to the 11th. It's not easy to compress steel. It's much easier to compress water. It's even easier to compress ethanol. So we can look at liquids and see how compressible they are under a lot of pressure. And so obviously, way down in the ocean, water is denser because it's under a considerable pressure. Although this is a huge number, it takes a lot to compress it by any reasonable value. Now the units are all, for all of these constants, for Y, S, and B, are all in pascals or newtons per square meter. And you can see why that's true. This part is always dimensionless, this part is dimensionless, and therefore we're going to have a force per unit area, which is a pascal. So these constants are going to have the value of pascals for their units. So we can say in conclusion that Y, S, and B, that's the Young's modulus, the shear modulus, and the bulk modulus, all have units of Pascal, which is the same as a Newton per square meter, or pressure.